Okay guys, today we're going to go over a hypothesis test for two means. I should have also posted the key to your notes on your Google Classroom, so if you want to, you can go through and follow along with that as well so that you don't miss any blanks. Today we are going to use our data from the New England Journal of Medicine, and actually Mr. Saver from the notes or from Skew the Script actually had done research for this paper. So basically today we're going to talk about strokes. In 1995, a new drug called TPA was shown to improve outcomes in stroke patients. In the following 20 years, there were no major improvements in stroke care. Hundreds of studies were done, but none were breakthroughs. So with TPA, less than 40% of people who experience strokes due to large vessel clots regain functional independence or the ability to live by oneself, including shopping, cooking, maintaining finances. And the question here, could we improve care for the patients? So then comes along the stent, a metal mesh on a long wire, and it is placed in the blood vessel in the leg and advanced to the blocked brain blood vessel. And then this traps the clot, and we can pull it out of the brain to restore blood flow. So the modified Rankin scale is how we rank the measurement of stroke outcomes. So 0 would be no symptoms, 4 would be moderately severe disability, such as needing assistance walking, and 6 would be considered death. So if the stent works, it would move the patients down this scale. From here on, this scale is going to be referred to as a disability score. So as you see that, you will know. So for the study, let's say we have a control and a treatment, standard care plus standard care and a stent. We have 191 stroke patients. Those should be randomly assigned. So after random assignment, standard care would have 93 participants. Standard care plus the stent would have 98 participants. Then we can measure which group had a lower mean disability score. So today's key analysis will be, did the stent treatment work? The first thing we want to discuss is a two-sample t-test for a difference of means. So remember, per usual, we're going to go through an informal version of this hypothesis test, and then later you will be able to see the 4-step process. I'm going to skip that in the video because I will post the key to Google Classroom. I would suggest that you try that on your own and then compare your results with the key. So here are our results. You'll see that we have the results for the stent, the results for the control group. Each has mean disability, each has a standard deviation, and both of them include our sample size. So if the stent works, the treatment group should have a lower average disability score. And you'll see here that that should mean that mu of S is less than mu of C. Now we do not know the mean of the population, however, we can see the mean of the sample. And that is given by X bar of S is less than X bar of C. You will see that the stent actually does have a lower mean disability score than the control. 2.26 is less than 3.23. And there's a difference of about 0.97 to the left, and that's where that negative comes in. So that's almost a full point. But there's a lot of variation between patients, and we can note that there's less than 100 patients in each group. That's greater than our 30 for central limit theorem, but it is worth noting. So we want to ask ourselves, could the difference in outcome have happened by chance alone, or did the stents actually improve patient outcomes? We need to discuss our hypotheses first, so take default belief until evidence convinces us otherwise. Our null hypothesis then is that the current standard of care is best, and our alternative would be that stents improve patient outcomes. Now remember, we always need to discuss what our variables relate to. So mu of S is the mean disability score of all patients who receive stents. Mu of C is the mean disability score of all patients who receive current standard care. Now, if we want to put this in symbolic terms, we would say that mu of S is equal to mu of C for the null hypothesis, meaning the stents don't improve outcomes over the current standard care, so the mean disability score is the same in both groups. For our alternative, we want to say that mu of S is less than mu of C. This would indicate that the stents did improve care, so the stent group had a lower mean disability score. Now, if we want to put this in a more mathematically convenient format, we can get both sides related to 0. So subtracting mu of C, we get mu of S minus mu of C equals 0 for our null. For our alternative, you will see that the alternative is mu of S minus mu of C is less than 0. And just remember, the only reason we do this is because it is a more mathematically convenient way to write the hypotheses. So let's recall the logic of our hypotheses test. Remember, we want to start by assuming the null. Okay, I'm going to assume that stents do not help. And then ask yourself, if the null is in fact true, how likely is it that we've gathered data that says it is not? So here we say the stent group had much lower disability score than the control group on average. And then last, we will draw a conclusion. Under my assumption of no treatment benefit, our observed data is unlikely, so I reject my earlier assumption. But let's go through this mathematically. So here we'll talk about the calculations. Remember, we have our number line, so assuming the null is true, we will set our center at 0. We assume there is no difference in average disability scores among all patients who would receive stents or the current standard of care. Now, the study enrolled 191 patients, 93 were in control, 98 in treatment. And at this point, the sample size is, or at this sample size, what estimates mu of S minus mu of C are we likely to get if stents don't actually help? So this is where our sampling distribution comes into play. Let's find the randomized distribution of x bar of S minus x bar of C from all possible random assignments. And you'll see here, under certain conditions, we have a normal distribution. We are centered at 0 since the null assumes no difference between disability outcomes. And our typical differences we'd see between stent and control groups by chance alone can be calculated as seen. So here you can see that we have our data. We can plug in our sample sizes. Since we don't know the true standard deviation, we were going to use sample standard deviations, and this means we must use our wider t distribution to account for the extra uncertainty. Okay, for that reason, when we calculate it out, we've got a standard error of 0.258. This means we need to take into account the degree of freedom. So the degree of freedom, remember, we're going to take the smaller group and then calculate n minus 1. The calculator is going to do something slightly different than that, but that's okay. So our smaller group, or our control, is n equals 93, so we've got 93 minus 1 is 92. So now we have a t distribution because of using that standard error. And you'll see here we have a difference of negative 0.97. So if we plot that, you will see how far to the left we are from 0. So we need to ask ourselves, if the null is in fact true, how likely is the data that you've gathered? And here we can say how many standard errors away is it, or t-test statistics. So you'll see here our standard error is 0.258. 0.258 should gather approximately 68% of our data within those two values. So between two standard deviations, it's pretty unlikely. We get 5% chance to get a sample mean more than 2 standard deviations out from the center. But we were 0.97 away from the center to the left. That's what that negative indicates. So if we want to divide that by the length of one standard error, we get negative 3.76. So we are negative 3.76 standard errors away from the center. -2 standard errors we have deemed very unlikely. So -3.7 is extremely unlikely. Now we can discuss the probability of getting this result, or more extreme, with the p-value. So the probability of being equal to or less than 0.97 away. Remember, this can be done in the calculator, and you can see that on your 4-step process page. But we will get a p-value of 0.0001, which is extremely low. Remember, we typically compare our p-value to our alpha level of 0.05. So compared to 0.05, we have a very small p-value. That means it is very unlikely. So recapping the test, is there convincing statistical evidence that the stent lowered the average disability from stroke? Assume the null is true. How unlikely was our sampled data? If our sampled data was very unlikely, if we assume the null is true. Therefore, we can draw a conclusion. Under my assumption that stents provide no added benefit, the actual observed data, 0.97 point decline in disability in stent group, is highly unlikely. The p-value is equal to 0.0001. So, I reject my earlier assumption. There is convincing evidence that the stent lowers disability from stroke. Okay, now that we have gone through those notes, I know I went a little bit fast, so you can always refer back to those if you need to, but I want you to try the 4-step process on your own and then go ahead and check your work with the key.